section for chapter 15 is about acid-base indicators, which we've used these before back in chapter 4. So there's two common methods for determining the equivalence point when you are doing an acid-base titration. One is to use the pH monitor and then pH meter to monitor the pH and then plot the curve of the titration. And the center of the vertical region of the pH curve indicates that equivalence point. Another way to do it is to use an acid-base indicator, which marks the endpoint of the titration by changing color. So, although the equivalence point we can define by stoichiometry is not necessarily the same as the endpoint, where the indicator changes color. So we have to be very careful about which indicator we use to ensure that the error is negligible. The most common acid-base indicators are complex molecules that are also called weak acids. So we're going to just call them HIN, IN standing for indicator. They exhibit one color when the proton is attached to the molecule and a different color when the proton is absent. We've used phenolphthalein before, and phenolphthalein is colorless in its acid form when it has the proton, and then when it loses the proton, it turns into its pink form. For any indicator, since it's a weak acid, we can have an acid dissociation equation. And rearranging the equilibrium expression for Ka, we can have that the Ka over the H plus concentration is equal to the concentration of the conjugate base over the concentration of the acid, the indicator. For most indicators, about 1/10 of the initial form must be converted to the other form before a new color is apparent. So we can kind of say that this is equal to 1/10. And that's going to help us in example 9. So for example 9, brothymal blue is yellow in its acid form and blue in its conjugate base form. Suppose we put a few drops of this indicator in a strongly acidic solution. If the solution is then titrated with sodium hydroxide, at what pH will the indicator change color first be visible? So we will have our acid equation that we saw previously up above, where we break down into the proton and the conjugate base. Okay, and we have a Ka that's 1.0 times 10 to negative 7 for brothymal blue, and that's equal to the H plus times the ion minus all over the acid form's concentration. Okay, well, we are assuming that it takes about 1/10 of the initial form to be converted, so we can plug in a 1 for the base form and a 10 for the acid form, and so that will kind of give us that 1/10 ratio. Okay, and so then by solving for H plus, we find that the H plus is 1.0 times 10 to the negative 6 molar. So then to find the pH at which the color change is first apparent, we just take the negative log of that, and the pH is 6.00. So this is telling us that at a pH of 6, we will be able to see the visible change when you're titrating the sodium hydroxide with the strongly acidic solution. The first color change will happen at a pH of 6. The Henderson-Hasselbalch equation is very useful in determining the pH at which an indicator changes color, and this is why we have that assumption that the base over the acid is a 1:10 ratio. But when we have a basic solution titrated, the indicator will initially exist as the conjugate base in the solution, but then as acid is added, more of the acid will be formed. So in this case, the ratio is actually going to be 10:1. So just pay attention, is it the titrating the base into the acid or the acid into the base? That's kind of important. This picture, this graph kind of thing is on your text, in your textbook, page 746, is going to help you you with your problems. And this kind of shows the color changes for some very common indicators and what colors they'll be and at what pHs they'll be. And so we can use this to help us pick out which indicator we should use so that we can see when this equivalence point is happening. When does the color change? When you're doing a strong acid, strong base titration, the indicator color changes will be sharp, occurring with the addition of a single drop of the titrant. So many suitable indicators can be used, but you want to make sure that you can see that equivalence point and that change in color. And so most indicators with this kind of titration will have endpoints as far away as a pH of 5 and a pH of 9. If you had a weak acid and a strong base, which we also do very often, there's a small vertical area around the equivalence point for this type of titration compared to the strong. So to choose an indicator, we have to pick one whose useful pH range has a midpoint that's close to the pH at the equivalence point. So then it's easier for us to see. So that's it for level 71. Our problems for the homework are number 69, 70, 72, 73, for 59 only, 78, and 80.